So welcome Alice Medvedev from the City College, and she's going to speak on dimensions of difference algebraic groups.
Thank you for the invitation. I'm going to start with computations and then go back to motivations and sort of the background setting and why I'm interested in this. So that I think in the beginning, when people are still slightly fresh, they will actually follow what I'm doing, and then the storytelling will come once you're actually tired. So I'm going to give sort of a bare minimum background, and then later come back to fill it in a little bit more. So my basic quest for the day is to try to understand some notion of dimension. And it's going to have to do with difference groups, and this notion of dimension happens to be the same as the length of, let's say, a maximal chain, or perhaps I should really be saying maximal length of chains of infinite index difference algebraic subgroups of what? Well, of the difference algebraic group. It's really very unfortunate. The difference and differential begin with the same letters, so you can't call these things D groups. And I don't want to look at all possible difference algebraic groups. In my setting, the study of difference algebraic groups can be essentially reduced to the study of things of the following form. Difference algebraic group defined by a very particular shape of a solution. Sigma is going to be my difference operator, just as in Michael's talk. So I'm going to ask that sigma of x should be equal to phi of x, and that x lie on G, where phi is a algebraic group morphism from G to, if x lives on G, then sigma of x is going to live on sigma of x. And I want this to be an algebraic, not difference algebraic, but just algebraic group homomorphism. So let me make some comments about this. In some sense, this sort of encoding of a difference algebraic group by two objects purely from algebraic geometry, this is the same sort of thing that has already happened in a few talks. We understand something about algebraic geometry, we try to leverage that knowledge to understand something about difference algebraic geometry. In some sense, this talk is, say, about completely different objects than what Michael Wimber was talking about, because notice that this immediately forces, I don't want this to be sigma, I want this to be sigma to the nth, but whichever way I do it, this forces the nth iterate of x to already be algebraic over x, in this case single valued. So in particular, the sort of difference dimension that Michael Wimber was talking about is going to be 0 for these things.
But you want an n over there as well?
Yes, thank you.
So n is fixed, uniform?
No, actually no.
Depend on x?
No. So the data phi, g, and n give some sort of a difference algebraic group, and then X is a point that might or might not live on that group. say, in the same way as in Omar's talk, the number of derivations was not fixed in the world, but certainly for any particular problem, you fix the number of derivations. Fine. Okay, so I should say something about what kind of difference algebra am I actually thinking about. I'm entirely avoiding the problem with perfect ideals, not perfect ideals, difference rings. I'm working over a field K. I'm working with an actual automorphism of the field K. This is something that's extremely significant. To make this talk sound more reasonable and have fewer exceptions, I'm going to work in characteristic 0. Something similar can be done in characteristic B, but I don't want to go into that for now. And I'm also going to have in the background some sort of an enormous universal domain. So I'll probably refer to it as U, contains K, let me say, huge. Just as for differential fields, there is a notion of being difference closed, existentially closed in extensions, that sort of thing. Basically, just as the intuition is the same as for algebraically closed fields, any system of solutions that has any hope, any system of difference algebraic equations that has any hope of having a solution, has a solution. And another technical condition that I'm going to take on these groups is I want these groups to have nothing to do with the constants. Constants meaning the fixed field of sigma. So let me say that I want this guy to have nothing to do with the fixed field of sigma. In particular, this excludes linear difference groups. So again, a very different setting from many of the earlier talks. In particular, this means that the underlying algebraic group is not going to be some sort of an interesting linear algebraic group. So in particular, this means that G is going to be built from the multiplicative group and abelian varieties. Abelian varieties are actually not such terrifying things, as long as...
What is nothing to do?
Formally orthogonal to.
But in more common language.
In a more common language, let's say that there are no non-constant functions from G to the fixed field. That is good enough, I think. Even with parameters from anywhere. So let me give an example of the sort of thing that that I'm interested in. So, and this is really the example that I'm going to spend some time talking about because it's, in some way, it's a special case, but other cases work very similarly. I'm going to just look at the situation where my group is the multiplicative group, and well, there aren't so many algebraic endomorphisms, so I'm going to pick one of them. It's just going to be x to the r, and in order to have nothing to do with the fixed field, I want to make sure that my r is not plus or minus 1. And unlike differential algebra, where the operator kills a whole lot of things, sigma is, for me, an automorphism, so it doesn't kill many things at all, so I want to also exclude 0, because then my whole group would have only one point, and that would be a little boring. Okay, so this is a canonical example. Hopefully that answers the question of what does having nothing to do with the fixed field mean. Any more questions so far?
What is sigma here?
Sigma is
No,
And
in,
what
the,
more is
in,
of
in,
my
in the example, in your example.
In my example, so this is the algebraic data,
Yeah.
and the difference equation I'm interested in, so my difference algebraic group is defined by the difference equation, sigma to the nth of x equals x to the r.
Oh, to the different. Okay.
This is both sides of the equation and the morphisms of the multiplicative group, so the set of solutions to this is going to be closed under multiplication, so this is going to be a subgroup of the multiplicative group.
Yes, and what did you mentioned something that the groups are not linear. In what sense?
This is not a sub. This is
Because this is a
Yeah,
linear,
it is.
it's a linear difference algebraic group.
Over k of x, but here x is the variable.
No, over k of x over q.
No, but
Over q.
But she means what they're equal.
but
The
she
subgroup. The subgroup.
We define the
So,
equations over q.
so for me, linear means a linear
Yeah, the
operator, and
Ah,
raising
ah,
to the rth power when r is not plus minus 1.
That's
is
what
not
you meant
linear.
linear. Okay, so
Yeah, I guess.
for us it means it embeds into GLM.
Okay, so,
Subgroup of GLM given by difference algebraic equations.
but they don't have to be linear?
But they are not linear.
No, they are all sorts of like SL2. It's a linear algebraic group. It's given by non-linear equation determined plus one.
Okay, cool. Okay. So what do I really mean? I guess when it, for the groups that have nothing to do with the fixed field, the ones that live on the multiplicative group, you're right, they will embed in GLN, but they will always be commutative. The underlying algebraic
Well,
group.
because they're subgroups of GM.
Right, but what I mean is that you can't, if you have a difference algebraic group on GLN, which happens to have nothing to do with the fixed field, then the algebraic locus of this group is going to be a product of GMs, so it's going to be commutative. So somehow the interesting linear structure of GLN is never going to play.
But by linear you mean on the equation, right? The equation
Yeah, I
is
mean,
not linear.
Yeah, I mean the equation.
Yeah,
is
so
not
solutions
linear.
do not live inside
Yeah.
the fixed field.
Yeah.
So if I take R to be 4 and N to be 2, would it say that sigma x is x squared?
So if R is 4, I like this example, I think I have it written down on my piece of paper. If R is 4 and N is 2,
Okay.
so what does this say? This says that sigma square of N is equal, of X is equal to X to the 4th. So this tells you what the second transform of X is in terms of X. It does not say anything about the first sigma transform. So, in particular, but there is something that it could say. So, let's call this guy, I need a name for this.
H.
No. H is not. I'll use curly letters to denote difference algebraic things and block letters to denote algebraic things. So, note now that what you pointed out is that sigma of x equals x squared defines H, a subgroup of G.
Okay.
This guy decides what to do with sigma of x, whereas this guy didn't know what to do with sigma of x. So the index is definitely going to be infinite. So, let me say inf. So in this example, I'm going to denote this length of this maximal chain suspiciously by SU of curly G.
And the index in your context means
index of subgroups, number of cosets.
Yeah.
So it follows that this length of maximal chains of infinite index subgroups for the group G is at least 2. Because of course I can always take
At least
is at least 2. Because of course I can always take the 0 subgroup, or the identity subgroup, the 1 subgroup in this case, as an infinite index subgroup here. Okay, excellent example. So, maybe obvious questions is, first of all, in this example, is it equal to 2? And another example is that you suggested this with the intent of looking at that. What if one doesn't have ulterior motives and just sort of randomly writes down something like, I don't know, sigma to the 17th of x equals x to the 15th? What's going to happen there? So, there are a couple of things to notice. Let me see from where I want to approach this. So let's have a vote. Who thinks that it's 2? Who thinks that it might be bigger than 2? 1-0 looks like a soccer game. The scores are too low. But why should it not be any bigger than 2? Well, think about what kind of new restrictions new difference equations do we need to impose to get an infinite index subgroup? If we impose somehow no new restrictions on, if we try to impose new restrictions on these two guys, then we'll have a problem with one of them becoming algebraic over another. So that's going to collapse the whole group down to something of dimension 0 already. On the other hand, if we impose conditions on how further iterates of sigma that don't impose more conditions on this one, it turns out that that cannot contribute to infinite index subgroups. It might contribute to finite index subgroups, but not to infinite index ones. So somehow, each time we find an infinite index difference algebraic subgroup, we have to bring down the number of transforms that are related to each other. So this is somehow the transcendence degree of the, so let me say, make this space, so let's call this a proposition. Of course, everything I'm saying so far is quite well known, except perhaps for my choice of names, or well known and obvious, except perhaps for my choice of name for this strange invariant. That may be a little less obvious. So let me say that if H is an infinite index subgroup of G and both are difference algebraic groups, then if you look at the field, you can think about this as a field of functions on G or as the field generated by a generic point of G. And you look at K sigma of H, they're going to be related the other direction, so like this. This is going to be a transcendental extension. Or I suppose I should say non-algebraic, is not algebraic. Notice that the kind of equations I started with forces these fields to have finite transcendence degree over K. And here, my transcendence has to go. Do I have it in the wrong order? No? Okay. So here, my transcendence degree has to go.
Yeah, you do.
I do have it in the wrong order. Okay. Has to go down each time I define an infinite index subgroup. So this can only happen finitely many times and only as many times as I have transcendence degrees. So let me note. So it follows that this SU of G is going to be bounded by this n times the dimension, the algebraic dimension of the underlying group. So dimension algebraic of the algebraic group.
It's still the inclusion.
Yeah, it's
Sorry?
The inclusion is still strange.
is it
Inclusion is still strange. If H is a subgroup, then
It's for the quotient, okay, but not for the inclusion.
Therefore, A should be a subfield.
Okay.
The generic point of
right?
H is a specialization of the generic.
well, maybe it's an embedding or something.
the transcendence degree of this thing over
G
K
is a
is
specialized.
greater than or equal to than the transcendence of
H is a
degree of this
specialization of G.
thing
No,
is
the other
over
way.
K.
No, no,
The bigger one, specialized
It was
in the bigger
incorrect as
things.
it was written. It's for quotients, you can...
Oh,
I'm
okay.
not going to worry about that.
Oh, that's fine.
This is what I want from it.
And this is because the specialization, right? H is specialization.
So let's look at something like this and try to figure out what can we possibly do with it. And I'm going to do sort of the schizophrenic thing of writing down notations for the full generality and actually only thinking about one specific example. So what do I have? I have my algebraic group G. And somewhere here I have the sigma nth twisted copy of it. What is this? You can think of it as taking the group G and applying sigma to the nth to all points, or you can think about it as defining the equations, taking the defining equations of G and twisting the coefficients by sigma to the nth. So, for example, I'm not assuming it's defined over the fixed field, though of course the multiplicative group is defined over an extremely fixed field. And what do I have? I have this algebraic map phi that is somehow giving me this difference algebraic group. And if I'm looking for an infinite index subgroup of this, defined by some difference equation, as we said, these difference equations are going to need to say something about sigmas of my point, probably of lower order. So let me write those guys in here. So I'm going to have a G sigma squared, that's up here. My new equation is going to involve some of these things. Not all of them, because if I have something like all of these, I have multiple equations involving this guy and I can eliminate them. So somehow, I have some relation amongst these things, right? So what kind of a relation could it be? Well, if I want to get an algebraic subgroup, it means if I want to get a difference algebraic subgroup, then the algebraic relation amongst these things needs to be a subgroup. And for the multiplicative group, I know very well what the subgroups might be. They're going to be defined by monomial equations. So let's say that I have some W here, an algebraic subgroup of this product. In my particular example where G is just the multiplicative group, this W is going to be defined by some monomial equation, and I'm going to solve the monomial equation for the last guy. So it's going to be defined by something like sigma to the nth of x is equal to a product over I, starting with 0 and ending with n minus 1, of sigma to the ith of x raised to the power Ri. Now, this should look suspicious. Why should this look suspicious? I've said that I'm taking an arbitrary algebraic subgroup of this product, and the way I've written it suggests that the last coordinate is a function in the rest of them. That's a fairly special situation, but that is only an illusion, because of course these things should be rational, not integer. So in fact, in reality, of course, what I should be writing is sigma to the m of x to some integer power is equal to a product of these things to other integer powers. I'm going to write it this way because it's, well, you'll see in a moment why. So what does it mean that this W, and this is the right equation to think about as far as defining a subgroup of my original difference algebraic group? It means that this condition does not impose anything extra on the two things that we already knew about. Because if we impose new conditions on the relation between these two things, then we're in trouble, because we have one, we have a second one, and two algebraic equations to unknowns forces them to be algebraic. And so then, if we're looking for a maximally length chain, a chain of length 1 is not very interesting, or length 2 is not very interesting. So how do you figure out whether this imposes a new condition or not, or doesn't impose a new condition? This is somehow what I want particularly to talk about as far as this meeting is about algorithms and actual computations. So, let me say the question is, does W impose new conditions on x sigma to the n of x? And really the real question is when can we find a W that does not do this? Well, another way of thinking about it is, when is this W compatible with my original equation without collapsing everything? So one does the usual thing, which is to somehow prolong this W. What does this W do? It gives me this guy in terms of these people. Well, applying sigma to the defining equations for it will give me the next guy in terms of the previous people. I also get a relation like this. I also get a relation like this, and so on, until I get all the way over here. And the relation I get from this, from prolonging and iterating, should not be particularly different from the V I started with. Now that looks, because if it is, then I get a new relation on this guy, and things collapse again. I don't want things to collapse. This looks like a lot of bookkeeping. It looks like a matter of taking fiber products of correspondences a whole lot of times. But actually, it's just linear algebra with the rationals. So,
what kind of equation that would mean if m is 1?
If m is 1, this would say that some power of x is equal to some power of sigma of x. And then iterating it would be a matter of multiplying, or rather raising to that power, which means multiplying that power many times. So, one way to do bookkeeping for this is to say that if I take x, sigma of x up through sigma to the m minus 1 of x, and act on it, not additively but multiplicatively, so I'll put maybe a star here to denote this, by some matrix, I'm going to get out of this the shifted tuple. So what do I need to do to get sigma of x? I just need to work out the second entry here. To get sigma squared of x, I just need to bring up the second entry here, all the way down to the next to last line, which is going to do this. And then the final line, these are R0 through R m minus 1. Okay? So now it's clear how to iterate this, because iteration is just multiplication. I'm going to give this guy a name called m. So if I iterate this guy enough times, I'm going to end up over here. How many times? N times. So if I look at m to the n, acting on x through sigma to the m minus first of x, this should return sigma to the nth of x through sigma to the m plus n of x, right? On the other hand, according to phi, we know what each of these things is supposed to be. Somewhere back here, we had an equation with r. So this is what the second equation says, but sigma to the nth of x equals x to the r says that this is also supposed to be equal to x to the r through sigma to the nth of x to the r minus first minus ones, which is a matter of taking this same thing we started with, minus first of x, and acting on it multiplicatively by just a diagonal matrix with all the r's. So this matrix acting on these things is supposed to be the same as this matrix acting on these things, up to finite index business. Well, what does that mean? Remember, we took this W to be somehow the smallest we would take for this particular subgroup. So these x through sigma m minus first of x, if I take them from the difference group defined by W, are going to be algebraically independent. If they were algebraically dependent, we would take something smaller. So what does it mean that taking algebraically independent things and raising them to these funny powers is the same as raising them to these funny powers? It means that this matrix to the nth is essentially the same as the diagonal matrix. Now, this is a huge constraint. For one thing, this tells you something about the determinant of M. For another thing, this tells you something about the shape of M. For a third thing, M was this funny, very sparse matrix for which you can actually compute. In particular, for this question here, once you see what we're trying to do there, it's clear that nothing interesting is going to happen here, basically for the very intuition with which we used to come up with this example, basically because 15 is not the 17th power of a rational number. And 15 is also not the 17 over little mth power of a natural number for any m less than 17. So, at least for a single coordinate GM, you can do this. And now I'm supposed to have stopped talking about 5 minutes ago. So, am I going to say anything about... Well, let me first say that this looks like a baby example, but actually, in the cases where you're looking at a product of GMs, or in the cases where you're looking at the product of a billion varieties, it's not that much worse. It all reduces to linear algebra over something. Then something is the endomorphism ring of the original algebraic group. And for these groups, it's not too bad. So the worst you're going to get for an abelian varieties, it's going to be it's going to be a number. And there are things you can do with it. SU really means the Pascal ring. And it's actually deep and highly non-trivial theorems by Chatudakis and Khrushchevsky that in these cases, the Pascal ring going down is always going to be witnessed by not just difference algebraic relations on these first guys, but a subgroup algebraic relation. So this is why I'm only talking about groups in this setting. And I think I should stop.
So the equation that you wrote over there, well, to me it looks like just the Picard-Bezier equation with the companion matrix.
This is not the usual action. This is not multiplication by the rational numbers. This matrix has entries from the rational numbers, and I am raising the components to this power. This is a multiplicative action, not the usual action of a matrix on a tuple.
Okay.
That's why it's something different.
But it still look like that, right? I just say look like, I didn't say this.
Okay.
I mean, okay, so I mean, there's different operation on this,
Yeah.
on the matrix action. But it really looks like the companion matrix, making it, you know, Picard-Bezier theory. The second thing is I'd like you to maybe amplify a little bit. Suppose I have, instead of sigma square equal to negative 7 equals 4 and 2, make it 8 and 4. Then what is the limit? How does this change SU?
Okay. So first of all, a very naive bound is 8, because each time.
Oh, sorry, it's the other way around.
Should you do 4 and 8?
4.
You're in either way. Okay. So now I have a naive bound of 4.
Right.
That anytime I break it in any way, I need to decrease the transcendence degree, so it's definitely bounded by 4. The question is now, can I find a matrix with rational coefficients? This is sigma to the 4th, so 0, 1, 2, 3, 4. Either connecting these guys or these guys or these guys. To see whether I can do it with these two, I just need a rational number, so that when I cube it, I get 8. Okay, so it's at least 2, because I can get an infinite index, infinite subgroup. Can I get anything in between? Can I get a matrix in a 2 by 2 matrix of that shape? So can I get a matrix that looks like 0, 1, A, B, where A and B are rational numbers, so that when I iterate it once, it becomes a diagonal matrix. When I iterate it twice, it becomes a diagonal matrix with 8s on the diagonal. I think the answer is no, but one needs to actually compute. And then the same question for 3.
Maybe you really want 16 instead of 8.
If you get 16 instead of 8, then I can cut it down twice.
Okay. All right. When you say iterate, you mean what is
Prolong.
prolong?
Yeah.
Or when I was saying iterate the matrix, I meant multiply it by itself.
Oh, in that case, you just multiply by itself. Yeah, that's
Well, because look what I'm doing. acting by this matrix shifts my sigma by 1. So if I want to shift my sigmas by n,
Right.
I need to do it n times.
But you said the action is not just the vector multiplication.
But the action is multiplicative. So I'm the same.
So in other words, if you add one matrix another one on this, one after another, it's the same as multiplying the matrix first and then add on it?
Yeah. I mean, it's
I mean, that's natural.
that's
Since your action is a little bit different.
right. This is what I'm doing.
Oh, okay.
Right.
Yeah.
So if my multiplicative action is raising two powers in
It's
iteration,
a multiplication. Right?
then that's the same as multiplying powers. I mean, it's still GLN acting. It's just instead of acting on the usual way on the additive group of the field, it's acting on the multiplicative group of the field.
Oh, yeah.
Right, thank you very much.
And we should also thank our kind organizer.